Hello. Today I will describe you the laboratory works, laboratory work number 3 in particular, and so the algorithm is a set of steps that you use to solve a particular problem. So the solution for a particular problem, it may have many algorithms for solving. So in this case, we need to compare the algorithms on the basis of time. So here we have the time complexity of the algorithms. So another case is when we have the basis of memory the algorithms require, so then we have the space complexity. In this case, we have the time complexity. So if you have the input, then input goes to the algorithm and it produces the output. So the time of the algorithm, it largely depends on the input. On the input, that is, here we describe capital N. So in this case, let's have a simple example. If we have the search algorithm performs the search function, and we have the array of the length n, capital N, and the search is performed that the array is traversed element by element and searching for the element named x. So in case 1, x is the first element, so number of checks is 1. So this is the best case. Case 2, x is not present and number of checks is capital N, so it equals to the number of the elements in the array. So this is the worst case. So time complexity depends on the size of the input capital N. So because if the element is not present or is, let's say, the last number of the element, then that it is checked. So then we have the worst case, and we usually analyze both cases, best and worst case scenarios, but we largely analyze the worst case scenario because the element may be checked the last. So, and if we optimize the worst case scenario, the best case scenario is also optimized. So as you see here, the worst case scenario directly depends on the n, so on the number of elements in the array or in that algorithm checks. And in practice, the number of n, it is usually large, so we need fast algorithms. Now, rules of analysis. So primitive operations like assignment, calculation, indexing, calling, returning, they take unit of time. Here we have the example I is equal to 3. So the element I is assigned with the value 3. So this takes only 1 unit of time. In this case, however, it takes 2 units of time. 1 unit of time is for indexing. So the element A, which is in the second row and second column, the algorithm finds this element in that particular position and assigns the value 3 for this element. So in this case, it is the operations of indexing and assignment, so it takes 2 units of time. Now, example number 1, we have this example of the sum. So we are summing elements in the array from 0, from the first element to the last element. So it has the number of elements capital N. So the length of the array is capital N. So initially the sum is equal to 0. So this is only assignment operation 1. Now we have the loop here. So we have the loop and we have, so in the beginning I is equal, so for the elements beginning with 1, with the first one, in the array we are performing the operation if that element is less or equal to n. Then we adding this I plus plus means that we are adding 1 each time, and for those elements up to n, until I is less or equal to n, we are adding and performing the sum operation. So we are summing, yes? First element, then first plus second, then first plus second plus third, and we are returning the sum. So here for this loop, we have 1. So 1 is for this assignment, I is equal to 1. Now the number of times that your algorithm checks if I is less or equal to n is performed n times, and plus 1 is for, because let's say if you have 100 elements, so the program has to check 101 times, because at 101 time, at 101st time, it stops. So let's say if the array is very large, but you are interested in only 100 of elements, so then n is equal to 100, and let's say the array may be 100,000, maybe 100,000 of elements, so then you are checking until 100, and then adding adding 1 each time, and summing until 100. So then at 101st element it stops, it checks and it stops. And n also is added is in this loop for I plus plus, because it is, the addition is performed n times, because you're checking n up till n, so adding 1 n times. And now the sum is, here we have the assignment and calculation. It is performed 2n times, because there are n times summed and calculated and assigned, yes? Now returning the sum is 1. So if we add all these together here, we have 4n plus 4. So you see that it is linear function. Now if we have another example, it is more complicated example, when we add a variable called temporary, and this temporary sum, and then just sum temporary. These are additional lines that just make our algorithm more complex by adding these two elements, and then the complexity, it increases. You see 5n plus 4. Now if we draw the graphs of 5n plus 4 and 4n plus 4 in one graph, so then you can see that maybe here I will draw capital N, and this will be the time t. It's not very nice, but so in this case, we will have this blue function it corresponds to the first algorithm, 4n plus 4, and another one 5n plus 4. So you can see that they both grow linear, and but the difference between them is very slight. It's not very significant. So they both grow linearly. But if we have, let's say, make our algorithm more complex and we make some changes to it so that it goes quadratically, like you can see here, 5n squared. So in this case, when n increases, the complexity of the algorithm is increasing like this. It takes much more time to be solved. So we are mostly interested in how the algorithm grows, if it grows linearly or if it grows quadratically or in some other fashion. So in this case, we are interested in this for n, or basically n, here 5n, and here we are interested in 5n squared. So if it grows linearly or if it goes quadratically. So this is what we are interested. Now, the big O notation. So here the big O is designed for showing what I told you before, whether the algorithm time function goes linearly or whether it goes quadratically. Here we have the function 5n plus 3 that goes varies linearly. So we say that this function is on the order of the complexity of this kind of complexity is on the order of n, that it goes linearly. This kind of complexity, however, is on the order of n squared, of quadratic complexity, because we have 5n squared plus 1000n plus 3. We don't worry about these constants, neither here nor here. In this case, we are interested in this linear part, but in this case, we are not even interested in this linear part, because we have the dominant term, 5n squared, that has that when increasing n is increasing in the fastest manner, like you see here. It's increasing in the fastest manner here, n squared. So the big O notation tells you the order of which the time complexity function grows. So usually the big O notation is defined as fx is the big O of gx if gx is greater after x is bigger than some point x naught, then fx. So then this gx is the order of fx. So gx is the upper bound of fx. So of the curve fx. So in this case, in example with linear function, so the order of fn is linear, and the order of this quadratic function is n squared. So we are usually comparing the algorithms on the basis of big O. Now we have the sorting algorithms, that your task is with sorting algorithms. So you can see we have simple sorting algorithms here. So bubble, insertion, selection sort algorithms. These algorithms in the, let's say, worst case, median case, and best case, let's say in the median case, they have n square complexity. Other sorting algorithms, in general, they take less time to be completed. logarithmic complexity is faster than quadratic complexity, so it takes less time. So your task is to choose one of fast sorting algorithms and one of slow and compare them. So selection sort algorithm has the complexity of n squared, and you can see the graph. It grows quadratically increases like this. So you can see that when you increase the n, when you increase the number of elements, so then the seconds necessary for it to be completed increase rapidly in the y-axis. In x-axis, increase the number of elements in the array. In y-axis, the seconds time, the time in seconds, yes, for the algorithm to be completed on that particular size of array. Now here you have the logarithmic type complexity. So you can see when you increase the data amount, so the time grows rapidly at first, but then it goes from, let's say this point is probably 50 elements, it increases like in linear fashion. So this algorithm is faster. And if you compare all of them, so you can see that bubble sort and essential sort, they take, when you increase the number from 1,000 to 100,000 to 300,000 number of elements in the array, data elements just simply, your bubble sort algorithm is increasing quadratically. In essential sort also increasing quadratically, but it is a bit faster, whereas quick sort is much more faster than all of them. You can see the green curve is stuck to the zero value of time in seconds. So you can see it is much faster than all of them. So this kind of curve, this kind of figure, you need to obtain in your laboratory works. So this is the final, it has to be in your report. So red or blue and this green. Yes, so compare fast algorithm with slow algorithm for sorting. So good luck.